what does a cycloalkane actually look like? When we learn about alkane conformations and about cycloalkanes, we naturally see them drawn out in these flat planar shapes. But of course, we know that this shape is not possible. We don't get our ideal angles in a flat planar shape. We get a 120-degree angle instead of our target 109.5 degree angles that we like to see in our tetrahedral carbons. So the question is, how can we bend this shape in order to get the right shape for our normal tetrahedral carbon bonds? To get into this tetrahedral shape, we're going to end up twisting our planar cyclohexane into what we call a chair conformation. So we're going to use our, similar to how our alkanes form a staggered zigzag, we're going to try to zigzag our lines in this cyclohexane. So we've got our zigzag going, but now of course we need to connect the other side of our ring. So we're going to kind of zigzag back to get what we call our chair conformation. So all of our carbons are in a zigzag, but now we're zigzagging around in a cycle instead of just going in a straight line like we would if we had hexane. So we're essentially just bending that hexane back and connecting it into our cyclic shape. Now, what's the significance of this jagged shape? So as we learned with alkane conformations, in order to get our more stable conformation, we want to change our shape to make all of our bonds staggered relative to each other. So let's take a look at our chair here to see what our bonds look like. So I'm going to take a look down this bond. So I'm looking from this carbon down towards that carbon. And at the same time, I'm also going to be looking down this bond as well. So I'm going to look head on at both of those two carbons. And we'll try to see what our conformation looks like for our cyclohexane. So if we're going to be looking down bonds, of course, we're going to want to use our Newman projections. So I start by drawing my circle representing that bond in the back here, going from my carbon to the next carbon. And I'll draw an adjacent circle representing my front bond over here. So I'm representing both of those two carbon-carbon bonds. Again, looking at it from this perspective. So for both of them, I'm going to have 3 bonds coming out in the front. So notice this point here is the same as this point over here. Both carbon-carbon bonds come out, and they meet here at the left-hand side of that cyclohexane. In the back, my bonds are going to be coming up to a carbon up there. Right? So I'm looking at these 2 carbons in the back. I've got my bonds coming out at the back together to meet the back point of my ring. So this point here is the same as this carbon right here. Those bonds are coming together from these 2 carbons at the back, from behind my circle up to that high point of my ring. Now I'll go ahead and finish my last few bonds. These, of course, would all be connected to hydrogens. And so we see that this is a staggered conformation. So this weird zigzag shape, or the chair conformation, as we call it, because it looks kind of like a lawn chair. You'd be leaning back, sitting in the central portion. You could rest your legs up here, and rest your head back here. This chair conformation is preferred because it makes all of our bonds staggered as we look at that Newman conformation for our cyclohexane. Again, when we get staggered, we're able to reduce that steric repulsion. We're also able to stabilize our bonds through that hyperconjugation effect. So if we have a staggered conformation, what would an eclipsed conformation look like for our cyclohexane? So let's try to redraw this so that we can eclipse our bonds. So I'm going to go ahead and start with my Newman projection, because I know if I'm trying to get an eclipse conformation, I know my bonds have to be right on top of each other. So I'm going to have to bend this. So first I've got my bond in front connecting these two. Got my usual hydrogens. And now I know in order to eclipse this, my bonds in the back have to be going out at the same positions. So this would be my perfectly eclipsed cyclohexane. So I have the front and the back end of my ring lined up, along with lining up my hydrogens, so that everything is eclipsing each other. So if we try to translate this into our line drawing structure outside of our Newman projection, this would look something like this. Let's go ahead and change this slightly. There we go. So this is what we call our boat conformation. We call it a boat conformation, of course, because we get almost like this boat shape with my either end of my vessel on either side of my ring system as they're bent up into that eclipse shape. So the boat and chair kind of represent the staggered and eclipsed forms that we saw for our alkanes, but now in our cycloalkane form. We'll tend to prefer our chair because, again, we get that staggered conformation. Our boat we can bend into, but it's going to be much less stable because of that eclipsing within our bonds. Okay, so now we're going to take a closer look at my chair conformation. Now the first thing I want to do here is try to fill in my hydrogens around my cycloalkane chair. So we'll start out over here. So these bonds are kind of going one to the back, one to the front. You need to kind of imagine this ring in a 3D shape. So this front line should be kind of in a wedge shape, and the back line would be more like a dash going backwards. Now in order to form my tetrahedral shape, I'm going to end up with, I'm going to want to put one bond downwards to a hydrogen, and then one bond over to the left and slightly up as another hydrogen. So now I have kind of my tetrahedral shape here with my two hydrogens and my two carbon-carbon bonds. If I go over to the next hydrogen, in order to make that tetrahedral shape, I need one more leg to my tetrahedron coming out here to the left, and then my top leg sticking straight out the top. I'll keep going around. I get one leg coming straight down, one leg going up to get my third leg of my tetrahedron, and so on and so forth. Again, I add in one vertical hydrogen and then one pointing slightly out to the side to get my four legs of that tetrahedral shape. And the last one here in the middle, again I'll put my leg pointing straight up and my third leg here at the bottom of the tetrahedron. Okay, so now I've added my hydrogens to my cyclohexane structure. Now what you should notice is I have 6 hydrogens, one on each carbon, that are pointing straight up and down. I marked these in blue. These are what we call axial hydrogens, or axial groups on our cycloalkane ring. So axial groups point straight up and down. So they're on our pointing straight up in our y-axis. They're going to be pointing downwards if we're at a point of our cycloalkane that's coming down, and it's going to be pointing up if we're at a point that's pointing up. So if you look at our green line, we have a green arrow pointing down, so our blue hydrogen, our axial hydrogen, comes straight down. Up here, our green lines from our carbon-carbon bonds are pointing up, and so our axial hydrogen goes straight up. On the other hand, these pink hydrogens, notice, are always pointing kind of off to the side, but at an angle. These we call equatorial. These are our equatorial hydrogens. They end up kind of pointing off to the side so not quite directly to the side, but kind of pointing off to the side at an angle. Both. Now, for our ring structure here, so we start out with our axial and equatorial groups. These both have slightly different properties for our cycloalkane overall. So axial groups tend to be a little bit more crowded, right? So they can have some steric interactions between all of these axial groups on the same end of our ring. And we can also get some crowding going on between our three axial groups on the lower half of our ring. So if I take one of these axial hydrogens and I replace it with a methyl group, this methyl group is going to experience some significant crowding with those axial hydrogens. So we really don't want big things in an axial position because we'll have some crowding with our other axial groups. So if we don't want that carbon axial, that methyl group, what other option do we have, right? We already know that we don't like our boat conformation because the boat conformation is eclipsed. So what other possibility do we have besides having that methyl group in that unstable axial position? So it turns out we can do something called inverting the chair, or chair inversion. So as with alkanes, our chair is flexible, right? We draw it in this conformation, but our conformations can change, right? Just like we saw with our alkanes flipping back and forth between staggered and eclipsed. Our cyclohexane can also flip between this chair conformation. It could switch to the boat. Again, in the boat we would have our cyclohexane with both ends pointing up. We end up with kind of this structure here, both ends pointing up. But then once we get into the boat conformation, so the boat and chair, we essentially just have to bend one side up to get to the boat shape, and you would bend it back down to get back to the chair. Now what happens if we bend it up into a boat shape, and then bend the other side down into a different chair? So this is called chair inversion. So if we bend this side up, bend this side down, we're going to have our chair basically facing the opposite way. So instead of peeking up on the right side, it's going to peek up on the left side. And we get this sort of chair shape, right? So this end went up, this one went down. Now, if we take a close look at our carbon as it's moving, so this is going to be bending downwards, and in the end, we're going to end up with that pink hydrogen pointing straight down, right? Because this is bending downwards into my new downwards pointing shape. And my blue hydrogen is now pointing slightly up, but in an equatorial position. If we go over to our methyl group here, so this carbon is the same as that one there. As we bend this, this is going to get pushed up. I'm going to end up with my pink hydrogen pointing straight up, and my methyl carbon is still going to be pointing down, but it's not going to be pointing straight down anymore. It's going to be pointing off at that slight angle of my equatorial groups. And we'll see the same pattern repeated at each carbon. So our hydrogen is not axial anymore, it's now pointing slightly up to the left, and my pink, what was equatorial hydrogen, is now pointing straight down. I see the same thing at every carbon in the ring. So my groups just switched. My blue groups switched to equatorial, and my pink groups switched to axial. So when our chair is inverted, our axial groups become equatorial, and our equatorial groups become axial. So both groups will switch position. So what was axial now becomes equatorial, and what was equatorial now becomes axial. Of course, this is an advantage for us here, because now that methyl group, which undergoes steric crowding here in my axial position, we get some clashing between these groups in our axial position, is now pointing off to the side, away from the ring, in that equatorial position. So this ring structure over here is now more stable compared to this ring conformation over here. So similarly to my butane conformations, while both of these are staggered and are much more stable than my boat, so my boat is going to be the least stable, there's still a difference in stability between these two staggered conformations. So if I can get my larger groups equatorial, that makes it more stable. And if my large groups are axial, like they were originally, then it will be less stable. So whenever we invert our chair, we're always switching what's axial and what's equatorial. The important thing is to remember that what's pointing up stays up, and what's pointing down stays down. So we had our methyl group pointing down originally, and it's still pointing down in our final chair. It's just now down in that equatorial position instead of down and axial. We can see that repeated for all of our hydrogens, right? This one was pointing up and equatorial. Now it switches up here and it's pointing up and axial. So these two key points happen every time we invert our chair, right? All of our groups switch between axial and equatorial. Our groups that are pointing upwards stay pointing upwards, and our groups that are pointing downwards stay pointing downwards. This chair inversion then allows us to switch between our different conformations, our different chair conformations, and find that more stable chair conformation. If we have a methyl group, we can put that equatorial. Obviously, the larger your group is, the more likely that is to get placed in that equatorial position. For example, if I replace this hydrogen over here with a large carbon group, so I'm going to replace it with a large tert-butyl group. So now it's in the equatorial position. When I switch it down with my chair inversion, that's going to go right here in my axial position. Now with this group, since it's a much larger group, and it's in that axial position, we're going to see a lot of crowding here between my different axial hydrogens that are pointing downwards, as well as that axial tert-butyl group. So now, when I add this second group onto my ring system, it actually makes this chair conformation less stable. So this chair becomes less stable, and this chair now is more stable. So the chair that has the larger group equatorial is going to be more stable. We can use this rule if we have just one group attached to our cyclohexane ring, or if we have multiple groups. Right? In this case, we have multiple large groups, and we go with the larger group equatorial, and we keep that smaller group axial. If you only have hydrogens, then you don't have to worry about it. Both chair conformations are the same. But as soon as you start adding big groups to your cyclohexane ring, it will create a difference in energy levels between those different conformations, similar to what we saw with our larger alkanes as well. Okay, so with these three key rules, we can learn how to invert our chairs, and then also how to find that most stable chair conformation. This will have important implications for the behavior of our cyclohexane-based molecules. So it's going to change what conformation our chair tends to sit in, which can also affect the shape and reactivity of that substituted cyclohexane.